The following tutorial is based on the states of matter for chemistry, and I'm assuming that most of the folks that are watching this video have a basic understanding of the states of matter. Just as quickly a review of that for the high school chemistry student. So before we get into what matter is, let's talk about what is chemistry. And the general accepted definition is chemistry is the study of matter, its composition, properties, and structure, and any changes that that matter undergoes. So the next question is, what is matter? And matter is basically anything that has mass and has occupies space. Therefore, it has density. And in other words, it's the stuff that makes up the world. And mass is the measurement of this type of matter. And mass is it's not affected by temperature, location, or any other factor known to make measurements unreliable. So now we're going to talk about the states or phases of matter and what the general properties of these three states are. There's actually 4 states of matter, and I'll talk about that in a few seconds. So the standard student should know that the 3 basic states of matter are solid, liquid, and gas. And then we're going to explain them in terms of shape and volume in a few seconds. Our first state of matter is a solid. And the definition of a solid is a phase that holds its shape and has a definite volume. The particles are in fixed positions in the solid, and there's very little space to have between the particles. So here's a little space here, a little space, but there's not a lot of space. Also, the particles do not move from here to here or here to here. They do vibrate back and forth in their position, but they don't move in any place. So there's no translation in a solid, and that makes them very difficult. The fact that they have no free space makes it very difficult for them to be compressed. Our second state of matter is a liquid, and a liquid does have also a definite volume as the solid does, but it takes the shape of its container. And if you look here closely, you can see that there's a little bit more free space in between the particles of the liquid. And this allows them to be move inside the thing. So liquid particles do translate into the free spaces here. So there is some movement, slow movement in there. And this can be easily demonstrated by taking a stagnant cup of water, in other words, water that's been sitting around and has no motion from just being poured out of the tap, and putting a drop of food coloring in there. And the food coloring will easily disperse by itself over time because the particles of the water are moving and will take the dye particles with them. The other nice thing about a liquid is that you can use this to, since it doesn't compress, because it still has a little bit of volume, but not that much for compression. What you can do with a liquid is use it as a hydraulic liquid, and that's the way a car lift works in a mechanic's garage. They put a lot of pressure on the backside of the fluid. The fluid does flow, but it doesn't compress, and therefore when it comes up against the solid piston on the other side for the ram, they put a lot of back pressure on the fluid, and the fluid flows, pushes against the ram, and the ram moves up, and the fluid moves up with it to push the ram and your car onto the air so that the mechanic can work with it. And our last state of matter for the high school chemistry student is basically a gas. And unlike the other two, it has both no definite shape or volume, and it expands to fill its container. And the major difference between a gas and a liquid and a gas and a solid is that the gas is easily compressed. It has a lot of free volume that is not occupied by the particles, and therefore the particles can be compressed into this volume. So it's very easy to compress gas, and this is easily seen or demonstrated by if you go into a store to buy a balloon, they usually have a cylinder of gas there, and that cylinder probably has several thousand liters of gas compressed into roughly 50 liters of volume inside the canister, maybe even less than that. And so they can fill thousands of balloons of, let's say, 2 to 3 liter size of volume in the gas in the balloon. And the reason why they can do that is they can compress the gas so much that they can actually put a lot more gas into a cylinder than it would occupy at a standard state. Okay, now that we know we have three types of the states of matter, solid, liquid, gas, we're going to talk about a set of characteristics by which the substance is being recognized. And these will fall into two types of properties, both physical and chemical. Okay, now that we know the three states of matter, let's talk about the physical properties of matter. And physical properties are observed without altering the identity of the substance. So these would be, for example, density, color, melting point, hardness, and conductivity. So no matter where on Earth you put the substance, the density doesn't change. If you crush it, break it, bend it, all that, the density still doesn't change. Color doesn't change, melting point doesn't change. And then the hardness and conductivity. Hardness being a measurement of the resistance to localized deformation, and conductivity could either be electrical or thermal conductivity. All these properties do not change in a substance when you physically alter the appearance of the substance by either beating it, crushing it, grinding it, things like that. Chemical properties, on the other hand, can only be observed by altering the composition of a substance. So you're actually going to change the substance to observe its chemical properties. And the couple of examples of the chemical properties would be flammability and reactivity with another substance, or the ability to oxidize or things like that. Okay, as we mentioned before, physical properties and chemical properties, physical changes do not alter the identity of the substance, and these involve crushing, tearing, phase changes, or dissolving. And phase change, you have pH here and pH here, so you can think of a physical change as a phase change. That's just a phase change. And chemical changes, these are changes that will alter the identity of the substance, and a new substance is formed. And this would involve burning, cooking, or chemical reactions. In addition to physical and chemical properties, we also have intensive and extensive properties. And intensive and extensive, the difference between the two is one depends on how much material you have, and the other one does not. So an extensive property depends on how much sample you have, so how much of a particular sample on hand, and then the intensive does not. So it does not depend on how much sample is present. Examples of extensive properties are volume, mass, and weight. And intensive properties would be melting point, boiling point, and density. The melting point and the boiling point won't change if you have 1 gram or 1,000 grams. The melting point and the boiling point stay the same. The density does stay the same also. However, the volume, mass, and weight will depend on how much material you have on hand. So now let's look at one of the intensive property of density. So let's look at density. And the definition of density is the amount of stuff in a given space. And we already defined that stuff was equal to mass in a given space, and so a given volume, right? So the more correct definition is it's a ratio of mass to volume. And then here's our formula for that. And it's odd to look at because these two things here are extensive properties. Yet density is an intensive property. This is an intensive property. And the reason why that the intensive property results from these two extensive properties is because it's the ratio. And basically what it is the more mass you have of a material, it occupies a certain volume, and therefore the ratio doesn't change between mass and volume to give you the density. Even though you have more mass, you have more volume that goes along with that mass, so the ratio doesn't change. Now, a further way to classify matter is that it can be put into two categories. We have pure substances, and then we have these things called mixtures. And those can be further broken down into additional classifications. So we'll talk about that in a few minutes. So let's look at a pure substance. A pure substance is any substance that has the same properties, characteristics, and has identical composition. The other thing about it is, and this is key, is they cannot be separated by a physical method. So you can't separate them by further doing any type of physical process. So separating using a magnet to pull it apart, sieving it, grinding it, separating it by density, floating density in a media. So it just doesn't separate that way. They're all the same. And the only two materials that are pure substances are elements and compounds. Everything else is not a pure substance. So we already looked at what the definition of pure substance is, and one of them was an element. And as you know from previous science classes, elements are the most basic building block of matter, and they are substances that cannot be broken down by ordinary chemical change. So heating it, mixing it with different acids or all that, it's not going to change the basic elements that involve. So a carbon atom is always going to be a carbon atom, no matter what you do in it as far as a reaction, right? At some point, it doesn't go into another, let's say fluorine or something like that. It doesn't work that way. Carbon will always remain carbon, and an element can only contain one type of atom, right? So carbon, fluorine, they're different elements that contain only one type of element, one type of atom. And CO2, for example, is not an element. Even though it's made up of two different elements, this one and this one, it's not an element. So this would be something else. There are several elements that exist in the diatomic state, and this means that they are always bonded to themselves in a free state. And so, an example of this would be oxygen. And the other examples are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. Now these right here are most of the halogens. And then the other ones here are the common O2 and N2 are basically gases that are found in the atmosphere. So when you see these types of elements in their free state, you should always think that these are in the diatomic state, including hydrogen. Now, compounds differ from elements because they are made up of two or more elements, and the other thing that's unique about a compound is chemically combined in a fixed ratio, right? A fixed ratio and chemically combined. So, for example, carbon dioxide, CO2, always has a ratio of 1 carbon to 2 oxygen atoms. CO, which is a different compound, has a ratio of 1 carbon to 1 oxygen. The properties different from those elements that they make it up. Here's a good example. To make water, you take hydrogen gas plus oxygen gas and gives you water. These are very flammable when an ignition source is nearby. This is not very flammable. Actually, this is used to put out flames. So you can see that the properties here, the chemical properties here, are different than the chemical properties here, even though that these are made up of these two elements. Compounds can be broken down into simpler substances by a chemical change. So we can reverse this reaction. We can break down H2O back into its constituent elements with electrolysis. So they can be broken down by a chemical change, but they cannot be broken down by any other types of changes, a physical change, or anything, for example. Mixtures, on the other hand, differ from elements and compounds because they are a blend. They are not chemically combined. So they're not chemically combined. They're just blended together. So you would think something like salt and pepper could be physically combined, blended, but they're not chemically combined. And they need two or more substances to be considered a mixture. An example of a mixture is salt water or air, and both of these things can be broken down into their constituent materials by some type of physical means of doing so. So now that we know what mixtures are, let's look at the characteristics of mixtures. Unlike a compound where it's a fixed ratio, each substance in a mixture can be varied, right? So you can have, for example, the salt and pepper ratio can be changed easily by adding more salt, more pepper, and it doesn't change the fact that you still have a mixture of salt and pepper. The individual properties remain unchanged. So the salt properties remain the salt properties, the pepper properties remain the pepper properties. You haven't changed them by mixing them together, or blending them together, blending them together. You have not changed them. And you can separate the materials by a physical means. You could dissolve the salt in water and then filter off the remaining pepper that doesn't dissolve in water. And then you could recover the salt later on by evaporating off the water. So you can do this by a physical means. Whereas a compound, you can't separate it by a physical mean or an element. So there are two types of mixtures. Let's talk about the first one is with a homogeneous mixture. And this is where the components that make up the mixture are uniformly dispersed. In other words, wherever you take a piece of the pie, it's always going to look the same. A piece of the material is always going to look the same. And a homogeneous mixture is also called a solution. And there's some examples here: salt, water, or air. And then the other thing too about a solution, if it's a solid solution, so let's look at a solid solution, and that could be a mixture of, let's say, zinc and copper, and well mixed together so it's a homogeneous mixture on the micro scale, and that would be called a solid solution, or in other words, also called an alloy in metallurgy terms. And the other type of mixture is a heterogeneous mixture, and this is where the components are not uniformly dispersed, and so they're different. And so this is a pile of salt and pepper, right? A pile of salt and pepper. So if you made a salt and pepper, you would basically put some pile of salt and some pile of pepper. They're not homogeneously mixed typically. There's always going to be areas where there's more salt and or more pepper in another area. And so another example would be a chocolate chip cookie, where you have little chocolate chips in the cookie, right? And if you took a piece of the cookie here and you have no chocolate chip, it's going to look different than if you have a piece of the cookie here which has a chocolate chip. So recall that the heterogeneous mixture is going to be different throughout its composition.